What I want to do in this video and the next one is to give you a flavor of EUV, which stands for Extreme Ultraviolet Lithography. Many people believe that this is one of the greatest challenges facing the semiconductor industry right now. It's said to be the Achilles heel of scaling, where it takes down this otherwise nice, strong and plumb Achilles, and the biggest weakness right now is this extreme ultraviolet or the difficulty in getting to extreme ultraviolet lithography. What this image is depicting is the scaling of the wavelength that we use for lithography, or rather the absence of scaling of the wavelength that we use for lithography. So it shows that back around in 97 we switched to using this deep ultraviolet lithography, which is at a wavelength of 248 nanometer. This was enabled using a excimer laser using a krypton fluoride source, which I'll talk about more in a few minutes. And then back around 2001 to 2002, we took the next evolutionary step and moved to a wavelength of 193 nanometer, which was enabled using argon fluoride laser. And we have been pretty much stagnant since then. So in the last 10 years, there hasn't been any change in the wavelength of the light used for lithography. And the next step is not an evolutionary step. What we need to do next to scale the wavelength is to take a quantum leap and go from this deep ultraviolet to extreme ultraviolet wavelength range and go to a wavelength of 13.5 nanometer. And that's a huge quantum leap from where we are currently, that is 193 nanometer. So then we asked ourselves that how did we enable scaling in the meanwhile? You know, we all have seen the technology progress from 65 to 45 to 32 to 22 to moving to 15 the next year. So the last few videos we saw that we have been able to do this by essentially using double patterning, and going forward using quadruple patterning, and even going forward using quintuple patterning. That allows you to double your pitch or double your quadruple your pitch or make your pitch eight times if needed. So then we asked, do we really need to take this quantum leap? Do we really need extreme ultraviolet lithography? And the answer to that is yes. And the reason we need that is because Moore's law has always been a law about economics. It has been that scaling each technology generation, you get 50% reduction in your cost. You can put twice the number of transistors in the same area, and if you make the same chip, you reduce a 50% reduction in your cost. And that has been true up till the 90 nanometer technology. So going from 130 to 90, people did actually used to achieve close to 50% reduction in the cost. And that was till this wavelength of scaling was continuing. And from that point, we moved actually to using double patterning or using quadruple patterning and so on. And what we have seen is, since using this double patterning adds a lot of process steps. So last few videos I described that moving to using, say, a self-align double patterning scheme, you add 4 or additional process steps each time you do a double patterning, and more the number of double patterning steps you add, you increase your cost. And so when we move from this traditional wavelength scaling to double patterning, we see that the reduction in cost achieved actually went down. So instead of getting a 50% reduction in cost, going from 90 to 65 nanometer, people only achieved a 12% reduction in the cost. And that has also been marginally declining. And actually what this source says is that going from 32 to 22 nanometer, you actually increase your cost, because you're using so many of these double patterning steps that there's no reduction in the cost even if you scale your transistor dimension. So this double patterning or quadruple patterning has really put Moore's law on life support, and to get it out of there, get it back to a healthy state, what we need is actually going to extreme ultraviolet lithography. And extreme ultraviolet lithography, it has always been a moving target, so we realized that we haven't scaled the wavelength in the decade, and people started realizing that they really need to go to EUV back in 2003 time frame, and they said, okay, we'll be ready in 2 years time. EU will be there in 2005. All we need to do is fix the source and we'll be done. And back in 2005 they said, oh, the source is not really ready, and we also discovered that there are some additional problems that we need to fix in terms of the optics, but we'll fix it and we'll be ready in 2007. And then people came back in 2007 and said, oh, the source and optics are not really ready yet. There has been significant progress made, but they are not quite ready for volume production. By the way, we also realized that there are a lot of problems in the resist, and that requires a lot of development if you need to go to EUV as well. And then said, but we will fix it by 2009. And then people come back in 2009, they said, oh, the source and the optics and resist are not ready yet, but we discovered that there are additional problems that you get in the roughness of your resist if you do to extreme ultraviolet lithography as well. But they said, this we will take care of it, don't worry about it, by 2013 it will be ready. So there what we see is, first of all, it has always been a moving target since the last 10 years, and people have come to live with the fact that it has been a moving target. They have at least we now know that these are the main issues that we need to address, and hopefully, thankfully, no new issues will pop up, but you never know. So what I want to give you a flavor of course it has been a moving target, but that's not because it's not like the US Congress where they just like to kick the can down every 2 years. It's there's some real challenges involved in the physics. So what are some of these issues involved in the physics of extreme going to EUV or going to extreme ultraviolet light? So what I'm showing here is the different spectra of light involved. So anything above 400 nanometer is called ultraviolet. It goes into the visible or the ultraviolet spectrum. Anything below 10 nanometer is called X-ray radiation. Even between 400 and 10 nanometer, that's a wide range. So between 400 to 100 nanometer, this is what we call as deep UV light or DUV. And below, if you go below 100 nanometer up to 10 nanometer, that's what you call extreme ultraviolet light. And if DUV, it can say it has more resemblance to UV light. EUV has more resemblance to X-rays. And all this is governed by the energy of the photon involved at that particular wavelength, which is described by this nice equation that Mr. de Broglie himself described. And what it says is that energy is related to this wavelength by E equal to hc by lambda. And if you translate into some numbers for the light we are trying to study here, it translates into that it's related by this particular equation. So according to this equation, if you have a lambda of a micron or 1000 nanometer, that corresponds to energy of a photon of 1.2 eV. So what does it mean for the wavelengths that we are trying to study, or the wavelengths involved in lithography? So what it means for the wavelengths involved in lithography is I described to you that so far we have used this 248 nanometer or 193 nanometer of light, and we have used these excimer laser based on krypton fluoride or argon fluoride. And if you plug those numbers into this, if you plug this wavelength into this equation, what you get is for 248 nanometer, what we have is a wavelength which corresponds to energy of photon of 5 electron volt. Similarly, if you have 193 nanometer, it corresponds to a photon energy of 6.4 nanometer, 6.4 electron volt. And these are not very high energy, and they are not very harmful either. So if any of you have undergone a LASIK treatment where they use laser to fix your eye prescription, they essentially use this excimer laser at these particular wavelengths as well. So we know that you can't cause too much harm with them. But what extreme ultraviolet requires is that it requires the wavelength target there is 13.5 nanometer, and if you plug that into this equation, what you get essentially is the energy of 92 eV. So 92 eV is a lot of energy for one photon. My advice to you is if you see a photon with 92 electron volt of energy, try to get out of its way because it can cause you a lot of harm. But besides that, another problem with having this much high energy is now if you have a photon of energy of 92 electron volt, it will get absorbed by pretty much everything that you put in its way. So suppose you had if you want to focus light which has this high energy and you put a lens, most of the photons will actually not come out of this lens because most of them will get absorbed within this lens. If you want to reflect that photon using a mirror, you will again lose half of the light at this reflection because this mirror will absorb half of these photons. Similarly, if you generate these photons using a plasma source, that plasma itself will absorb half of these photons. So first of all, it's very difficult to generate these photons, and when you generate them, they will get absorbed by whatever that you put in their way to reflect them or to focus them.